And from the outlet of this heat exchanger, which is 10 centigrade, we want to remove the remaining water that's still present in this stream. We can use this component splitter to model our molecular sieve, since we want to remove water into the ppm level. You can use this specification parameter, and the splits you can use for respective components. As you can see here, you can follow me by specifying this type and then this number. For water itself, we want to decrease the water content at the ppm level to mitigate the possibility of dehydrate that could present in our system, since the CO2 will be stored at minus 20 centigrade. Then we can use this valve to represent the pressure drop that possibly occur since the gas passing through the molecular sieve, and we can specify the pressure drop at 8 per square inch as the conservative value. And we can see here there is this decrease of the pressure compared with the upstream of the molecular sieve, but actually the temperature difference is not significant. Afterward, we can connect the stream with the final heat exchanger to cool down the CO2. Can see the heat exchanger, and we can specify the temperature at stream number 17 at minus 25. So you can see our system is already converged. Which system is actually approximately 0 centigrade. We can adjust this value maybe in the end. So maybe I want to see the water content here, so table, and we can see the water content for overall. So as the HYSYS calculation, we obtain that the water content is approximately 0.7 pound per mmscf or million standard cubic feet. So we obtain that we can multiply this value by 21 and obtain the ppm volume, and we obtain that this specification is already satisfy our specification. It's actually 15 ppm. Okay, we can verify the temperature at this stream. It's actually approximately 0 centigrade, and we want to increase this temperature afterward, since we want to use the seawater as our heating medium to achieve the temperature that required by our consumer. Thereby, we need further heating, and we can use the seawater as heating medium. Then we can assume that the seawater consists of pure water without any impurities for the simplification for our study here. And also we can assume that the temperature is 35 centigrade. It's actually the water intake located at near surface of the water. And the pressure discharge, we can specify approximately 12.01 bar. And for the initial value, we assume that the seawater required is approximately 90 ton per hour, and we can adjust it later. Then we can connect this stream to the final heat exchanger, seawater heat exchanger. Afterward, the temperature outlet of this stream we will specify about 15 centigrade, and then with 90 tons per hour we obtain that the outlet temperature of this seawater heat exchanger approximately 25 centigrade, which actually still exceeds or still above the environmental constraint, which typically at the 10 centigrade we are allowed to discharge seawater from our system. Then we are going to adjust this temperature of this stream, which actually approximately 0 centigrade, by adjusting the C1 stream. You can add this manipulator, adjust manipulator, then connect this adjusted line here. You can adjust the mass flow of this inflow, the CO2 inflow, and then for the target variable we want the temperature outlet of the last heat exchanger is okay. Before we specify the temperature we decide, we can change the tolerance, which actually 0.01 is enough, and also the maximum duration is 100. Can specify this at 5 centigrade. So actually we try to specify the temperature outlet by changing the mass flow of CO2. We obtain the mass flow is approximately at 96 ton per hour of CO2 that can be liquefied here. So we have rearranged our simulation by changing the stream number and rearrange the position of the stream, and then the seawater is the same and the temperature is a little bit rise from the previous one. Right now is 28 centigrade. Actually you can change this, you can set the constraint for the temperature outlet here for the seawater by adjusting this mass flow. You can try by yourself in your simulation case. You can use this adjust manipulator, and you can change the mass flow so that the temperature of the outlet, seawater outlet, is exceeding your requirement or your temperature constraint. Let's observe this heat exchanger. The temperature of these streams, particularly for the C11, is approximately minus 25 centigrade, and at this pressure and this temperature the CO2 present at the liquefied phase. In this case I specify 25 centigrade in order to accommodate the pressure drop or the heat increase from the environment during the transfer process to the storage. So as the preliminary I specify this value by minus 25 centigrade. For the overall system, the LNG will be rise. The pressure of the LNG will be rise using these two pump, LP pump, low pressure pump, and HP pump respectively, to 65 bar in accommodate to the customer requirements, and will be heated using the CO2 from the liquefaction process here, and then will be further heated using the seawater, because actually it's still low temperature and we can utilize the seawater as our heating medium in order to achieve our customer specification. As you can see here, 15 centigrade and approximately 61 bar with the molar flow of 100 million standard cubic feet per day. So maybe that's all for the integration of the LNG regasification process and the CO2 liquefaction process. I hope this video is useful. See you.